Hi, this is Math 7, Unit 6, Lesson 18, Subtraction in Equivalent Expressions. And so one of the things we're talking about today is how do we work with subtraction in our expressions. And I think the key thing to remember from today's lesson, our takeaway is going to be that subtraction problems can be rewritten as adding the opposite. So for example, if I had something like x minus 5, I could rewrite that by saying this is x plus a negative 5. And so I can always turn a subtraction problem into an addition problem. Now in our number talk activity today, we have some sums or differences that we're asked to do mentally. So here I have a negative 30, and I'm adding that to a negative 10. And so in my mind, as I look at this, I know that the signs here are the same. So in my solution, I'm going to keep the sign the same, and I'm going to find the sum. So 30 plus 10 is 40, and I keep the same sign as a negative there. Right, and I could do the same thing if I use like a number line. If I thought about it like a number line, if I'm at 0 here and I go start at negative 30, right, I'm here, I'm going to add an additional negative 10 there, which means I'm going to go this way 10 more, which puts me at negative 40. Here, it's the same idea except we've changed the order around. So again, the signs are the same, so I keep the sign the same and I find the sum. 10 plus 30 is going to be still 40, so I'm in the same spot there. For this one though, I do have a subtraction problem, so I could rewrite this as adding the opposite. So negative 30 can become negative 30 plus a negative 10. So the opposite there of a positive 10, because it's positive there, becomes a negative. Now at this point I have the signs are the same, and I find the sum and keep the sign the same, so I end up with a negative 40 again. In this case, I have a 10 and I'm just doing subtraction. So if I want to add the opposite, this becomes an add, and the opposite of a negative becomes a positive. So that actually becomes add a positive 30, okay? Which then becomes equal to just a regular 40. So the first three are all going to be negative 40 in their responses, and the last one is a positive 40 there. This next activity is called a helpful observation. It says Lynn and Karen are trying to calculate this. Here's their conversation. Lynn says, I plan to first add 7 3/4 and 3 5/6. So Lynn says, I'm going to do this part first. So I'll start by finding equivalent fractions with a common denominator. That can certainly be done. No problem, you can do that. But it's going to take a little bit of work there. Karen notices that it will be a lot easier if we could start by working with the 1 3/4 and the 7 3/4. Can we rewrite that like this? Like that? Can you just rewrite that there? Lynn says, no, you can't switch the order of numbers in a subtraction problem like you can with addition, because 2 minus 3 is not equal to 3 minus 2. So you can't just move things around like they did there. And in this case, what Karen's doing is moving the numbers around, but keeping the signs exactly the same. Karen says that's true, but you remember what we learned about rewriting subtraction expressions using 2 minus 3 is equal to 2 plus a negative 3, right? So that's a good point they're both making there. So using that information of what they talked through in their conversation, let's take a look at that equation and see what else we could do. It says write an expression that is equivalent to this that uses addition instead of subtraction. So if we take our initial problem, we have 7 3/4 and we add 3 5/6. Can I turn this subtraction into an addition? Sure, I do that by doing what? Adding, and I always use parentheses, but you don't need to, adding the opposite, negative 1 3/4. At this point, I have numbers, here, here, and here, that are all joined together by addition. And once I have something as an addition problem, I can change the order around of those numbers and keep the signs connected to the numbers they're connected to. So if we rewrote the terms, if you wrote the terms of your new expression in a different order, would it still be equivalent? And the answer here is going to be yes, it would, but let's show. So here's what that means. If I did 7 3/4 and then I moved this bit over here to come second and made it plus, which it still is plus, negative 1 3/4. I'm not changing this number at all. It's still a plus and still adding the negative 1 3/4. And then we're still adding here, and now we take this bit and put it down here for 3 and 5 6. So in this case, by doing this there, yes, everything is going to work. I'm keeping the negative sign with the number that it goes with, but because it's opposite, I can use a cumulative property to then change the order around. And this does become an easier problem to do, because I could do this first, and 7 3/4 plus a negative 1 3/4. The 3/4 cancel out, and 7 minus 1 is 6. So I'm left with 6 plus 3 and 5 6. And 6 plus 3 is 9, so you end up with 9 and 5 6. That is certainly a much easier problem. I'm not finding a common denominator. It's easy to solve. So there are some advantages to being able to write a subtraction problem as an addition problem instead. Now in terms of organizing work here, here's some expressions dealing with kind of distributive property. So let's kind of back up a second here, because what we've talked about before with these like area blocks, because it's kind of the area of a rectangle here, is we've done things like this, where we had a block like this, and we had a 5, and we had a 3, and we called this a 2. And to find this area of this whole rectangle, we could do 2 times 5 here, and then 2 times 3 there, which could then all be the area. So the area, one formula for the area could be the area is going to be equal to 2.5 plus, oh, not 2.5, 2 times 5 plus 2 times 3. But another thing I could look at is that this top part is actually 5 plus 3 if I combine that together. So I can also say the area is 2 times 5 plus 3. And that's another equation that would be able to be utilized to solve for the area. So I could look at this box and write it a couple different ways. So in this case, it says write 2 expressions for the area of this rectangle. Okay. So I could do 8y times a half, right? And so I can do 8y times a half. Well, let's do it this way. First, we could do it with the half on the outside, and then we have 8y plus an x plus a 12. Okay, no problem there. That's one way of doing it. But I can also combine it in here. So 8y times a half, 8 divided by 2 is 4, and I have 4y. A half times an x is going to be a 1/2 x, and 12 times a half is going to be 6. So I can also write 4y plus 1/2 x plus 6. These are 2 different expressions that mean the same thing. One has a half on the outside, and if I distribute it through all the parts, I come up with this expression right there. Number 2 says, use the distributive property to write an expression that is equivalent to this. The boxes can help you organize your work. So, how would we write an equivalent expression? Well, 8 times a half is still going to be 4y, right? But a negative x times a half is going to give me a negative 1/2 x, and a negative 12 times a half gets me a negative 6, right? But what I'm doing here, in this case here, is we're going to still combine all these together. So I still end up with 4y plus negative 1/2 x plus a negative 6. All right, so that's what I get when I distribute things around. Then it says use the distributive property on this one to write an expression that's equivalent to that. Okay, so same idea. So we do 1/2 times 8, which is going to be 4y, and 1/2 times a negative x, which is going to be a negative 1/2 x, and 1/2 times a negative 12, which is going to be a negative 6. So that one works the same way. Now for both of those expressions, you really are dealing with the same thing. Look at this one here compared to this one here. 4y plus negative 1/2 x plus a negative 6. There's no major difference there. The difference here is I'm taking this subtraction problem and I'm turning it into add the opposite. And I'm adding the opposite, right? Which now matches what's over there. All right, so that's kind of how that works, the distributive property. You can have 2 ways of showing that, but it's helpful to be able to turn your subtraction problems into addition problems. All right, so So there is a little activity here called Are You Ready for More? And you have a calendar, you have the date, the 10th. It says look at the numbers above, below, and to either side of the 10. You have 3, 17, 9, and 11. Average those four numbers, and what do you notice? Okay, so to find the average, I'm going to take the 3 plus the 17 plus the 9 plus the 11. I'm going to take all those up, add them up, and I'm going to divide by the number of numbers, 1, 2, 3, 4. So when I add those up, this is 20 plus 20, which is 40, divided by 4. And 40 divided by 4 is equal to 10. Now what date did we start with? We started with the 10th. Well, that's interesting, isn't it? So choose a different date and see what you come up with. Alright, so on your own, pick a date, and then pick the number above it, below it, and beside it, and see what happens. I'm going to pick the number 20 real quick. So when I pick 20, my numbers above it and below it, I have 13 plus 27 plus a 19 plus a 21. I'm going to combine those and divide it by 4. Again, my number that I chose was 20 here. So 13 plus 27 is 40 plus 40 divided by 4, which is 80 divided by 4, which equals 20. So notice this matches again. Why is that the case? Why is that the case? And that's question 3. Why does that work the way that it does? We could think about it in terms of algebra. If the date we pick we call x. Now, if the date we pick is called x, what happens to our numbers? Okay, the number here, the number above it, is the value of x, 20 minus 13 minus, so it's minus 7. Then we're going to add to that a week later, which is the same date plus 7. Okay, so what's happening with the minus 7 and the plus 7? They're going to eliminate each other. When I look side by side, I have x minus 1 more day, and I'm going to add to it x plus 1 more day. So again, the negative minus 1 and plus 1 are going to cancel each other out. So what I'm left with really is simply 1, 2, 3, 4 x's, and because there are 4 numbers, 4x divided by 4 is going to leave me that x is going to always equal the same thing. So x is going to equal the date that I had to start with. Okay, so that's going to equal the date because it equals 1. So whatever it's going to be, the date's going to match up right there. So it's just a cool little algebra pattern, little trick there for how that works out. So in terms of our lesson summary for today, we could say that working with subtraction and signed numbers can sometimes get tricky, and we can apply what we know about the relationship between addition and subtraction. That subtracting a number gives the same result as adding its opposite. So subtracting is the same as adding the opposite, and that helps us out. So if I take a equation like this, and we turn, instead of subtracting 2/3, we turn it into adding its opposite, that's going to be very helpful. Once I add its opposite, now I have addition problems, and I can move the order around. I can take the negative 2/3 and the negative 1/8, and I can exchange places with them, keeping the negatives attached to that, so that I end up with 5/8 plus 1/8, right? This one went over there, and that one went over there. Now it's easier to do some computation at the beginning to recognize I have common denominator, and I can do 5 plus a minus 1 to get me 4 right there, right? And so that helps me kind of get some things going there. I can also then use some diagrams like this, and I can distribute to help me figure out how to also solve problems that require some multiplying of signed numbers as well. And that's really what we went over today. Let's take a look at your homework assignment together after you've done it on your own for a little bit. For each expression, write an equivalent expression using only addition. All right, so here we go. This is going to become 20 plus a negative 9 plus 8, and we're going to do plus the opposite, negative 7. You could leave it like that, or if you chose to put it in parentheses, you could do that as well. Okay, it's up to you for which way you want to write that out there. Okay, that's kind of how I write mine. Here, we would do 4x plus the opposite, negative 7y, plus the opposite, 5z plus 6. This one here, we don't have to worry about the first one because we're not adding it, we're just calling it a negative 3x, so we can leave it like that. But this term would be add the opposite. Here we're going to add the opposite, and here we're also going to add the opposite, negative 8/7 z. Number 2, use the distributive property to write an expression that is equivalent to each expression. So we're going to distribute, and let's see what we got here. So here we go, 9 times 4 is 36x. 9 times negative 3y is a negative 27y. And 9 times a negative 2/3, well, 9 times 2/3, that reduces to 3 times 2, which is 6, and it's going to stay in minus 6 like that. Here, negative 2 times a negative 6x is a positive 12x. Negative 2 times 3y is a negative 6y. And a negative times a negative is going to give me a positive 2 right there. On this one, 1/5 times 20. So 20 divided by 5 is 4y. And then 1/5 times a negative 4x will give me a negative 4/5 x. And 1/5 times a negative 13 is going to give me a negative 13/5. Can't reduce it, just is what it is. Here, 8 times a negative x will give me a negative 8x. And 8 times a negative half gives me a negative 4. And finally, a negative 8 times a negative x gives me a positive 8x. Negative 8 times a negative 3/4, 8 reduces to 2/1. So 2 times 3 is 6. It's going to be a positive 6y. And then here we have a negative times a positive, so I put a negative, and this becomes 56/2, which is the same as 28. So we have negative 28 there. Number 3, Kieran wrote the expression x minus 10 for this number puzzle. Pick a number, add negative 2, and then multiply by 5. Lynn thinks Kieran made a mistake. How can she convince Kieran that he made a mistake? Well, it might be good just to actually pick a number and try it out, okay? He thinks that this should work, okay? So let's see. Is this the same as this? Well, let's try a number like, let's go with the number 2. Okay, we're going to use the number 2. Let's use the number 2. That's our number. So with the x minus 10, if I put a 2 in here, 2 minus 10 is going to equal negative 8. All right? And let's compare that to versus over here, I take the number 2 and I add a negative 2 to it. So now I'm at what? 0. If I multiply that by 5, I'm at 0. Does this match that? No, it does not. Not going to work out too well. So that means that the expression doesn't actually work with this phrase right there. The correct expression should be something more like, you take a number, you add negative 2. That's like adding negative 2, and then we multiply it all by 5. So I could leave it like that, or I could distribute, and we could have 5x minus 10. And that would be the proper expression that would get you a number that would work. All right. And the last one, we have an output from a coal plant shown on a table, and also the output of a solar plant shown on a table. So we can see that they're both producing energy. We can see the number of days and the amount of energy that it's producing for both of these plants there. And so based on the tables, is the energy output in proportion to the number of days for either plant? So is there a proportional relationship between the energy and the number of days? So if there's going to be a proportional relationship, what we're going to see is that there's a number we can multiply across or either way in order to get the same number again and again. So we used to do that by doing the y over x, right? So we could take something like 2.4 and divide it by 1200. When I did 2.4 divided by 1200, I ended up with 0.002. If I do it down here for this one right here, and I did 20 divided by 10,000, I still end up with 0.002. And the same is true there. So I do have a proportional relationship when it comes to the coal plant and the energy produced versus the number of days. When I look at the solar plant, here's what happens here. I have 1 over 100, which is the same as 0.01. But then we can just go down right here to look at this one, which is 10 out of 1750, which is 0.0057. I already have a difference there. These are not proportional, are they? Right? Not proportional. So there's definitely a proportional relationship with the coal plant, and there's not one with the solar power plant. So is there an equation we can write there? There certainly is. Just depends on how you want to write it out there. What we've done before is we would take this would become our x and this becomes our y, typically is how we usually set them up, and we do y equals our k value times x. Now our y value here is the number of days, so the days is going to be equal to the k value, which is 0.002 times x, which is the energy. And that's one way you might have set it up. The other way that our kind of textbook is talking about setting up is to say, well, if we want to do it in terms of energy, you can actually take the energy amount, and to find out how much energy going this way you can get, you would take your days and multiply by a fixed number. In this case, 20 times 500 helps you get to 10,000. So you actually could write it that way as well if you chose to do it that way. So E would equal 500D. So 500 times the number of days will tell you how much energy output you're going to get. So that's the way the book kind of talks about doing it for your actual solution. This might work if you just did your X and Y stuff. You still end up with the same result. It's just in terms of which one's going to be your X or Y value. That's it for today, and we'll see you next time.